This is Solve It for Kids.
Hello, my amazing and curious friends. My name is Jennifer, the Dean of all things STEM and STEAM, and this is Solve It for Kids' 3rd anniversary. Woo! Woo! We are celebrating 158 episodes and over 50,000 downloads. Thank you so much for listening and enjoying our podcast that gives kids and families a peek inside the real world of scientists, engineers, and experts as they solve problems in their jobs using creativity, cooperation, and critical thinking. And now please welcome to the show my amazing podcast partner, Galactic Space Geek, Jeff Gagne.
Hello, Jennifer, and hello, listeners, and happy 3rd anniversary
Yay!
to us and Solve It for Kids. What an honor to be part of this podcast and to talk to so many scientists, engineers, and experts who share their passion and their love for their jobs and get us interested in what they do. And guess what? Today is no different.
Yes, this is a really awesome episode. What problem are we solving today?
Why does a spacecraft need a heat shield?
Why does a spacecraft need a heat shield? Oh, I feel an amazing space episode coming up. Who is our guest today, Jeff?
Jen, you must be able to see into the future, because this is going to be a great episode with Dr. Sarah D'Souza. She is Deputy Subsystems Manager at NASA Ames Research Center.
Welcome to the show, Dr. Sarah.
Thank you for having me. I'm glad to join you all.
Well, we are excited to have you here, not the least because Jeff and I are huge fans of Orion. We both saw Artemis launch in person, and I mean, it was amazing.
Yes. Wow.
I can imagine.
It was amazing. So we have followed the wonderful trek of Orion out and around and back. So we are excited to hear from you, but I like to start at the beginning. Did you always know that you were going to be an engineer and work on heat shields?
The short answer is no, but I like to tell this story. Gosh, it was when I was a college student still, and my family were going through old photos, and my sister, because I was working at Johnson Space Center at the time, still it's NASA in Houston, and she sends me a picture. And it's of my mom holding me. I'm still a baby, definitely less than a year. And behind her is a poster of the NASA space shuttle. So I like to say, and I'm sure my dad was taking the picture. And I like to say that I think from when I was a baby, this was my destiny.
That is fantastic.
Excellent.
Fantastic.
But all that being said, I think the turning point for me was when I was in high school. I joined the junior ROTC program, or Air Force Junior ROTC program. And there, I already had an interest in stars. I was already paying attention to the Mars robotics missions, Curiosity, all of those. But it hadn't crystallized in my head about my vocation.
Yes.
And when I was in high school, joining that program, there was a colonel who taught us all about aircraft and sort of the history of it. And and it was at that point that I was like, I want to be an aerospace engineer. And
that's awesome.
And from that point on, that was my goal. And then in college is when I really got excited, and it actually was something that I realized I could do, was work for NASA. It wasn't even, I knew NASA existed, but it wasn't even sort of in my mind. I wanted to be an aerospace engineer. I wanted to be an astronaut, but I didn't know the vehicles, right? I didn't know the
exactly.
How do you do that?
Yeah.
And so once I figured out, in college, once I got my Pathways internship with NASA Johnson Space Center, my fate
Wow.
was sealed. And I was like, yep, this is what I'm doing.
That's awesome. I love that.
Just for fun, I know we're going to talk about what you're doing now, which is super cool. Do you remember the first project you were working on when you got to NASA with that internship?
Yes. It's a great question, Jeff. It was the one beautiful thing, if anyone in college has the opportunity to do this, the Pathways program was really, really great because it gave me a breadth of opportunity to look at what did I want to do as an aerospace engineer.
Okay.
So this first co-op, I would have never thought I would have been there, but it was looking at or studying the systems required to do water filtration and recovery on board the International Space Station.
Oh.
So what was really, I had no idea that I would be learning about water filtration at NASA. I just, until you do things, you don't understand, right? So
Right.
it was
Sure.
just so, there I learned about the resourcefulness of our NASA folks. Like you can't just buy things all the time. So you go, what can I use in the lab? Learn from my mentors and my managers just about what lengths they go to take care of the astronauts who are on board ISS to make sure that we're utilizing resources properly. I mean, it was just a really amazing experience. And one of the fun things was because they've got this prototype water filtration system in a lab, you're recycling, bathroom water, shower water, washing your hand, right? All of those things. So they wanted you to, like, if you rode your bike into work, they wanted you to like take a shower in the lab. They gave them, test like the kind of water
materials.
You want to filter. Yeah. And so
that's fun.
There are multiple different ways to filter water. And that was actually the place that I learned, it's not just like, let's say the filter canisters we see in a Brita, right?
Right, exactly.
Sure.
There's anaerobic and aerobic bacteria that you can put the water through and they kind of take care of some stuff. You've got UV, all these things that you can, that you kind of piece together to make the water that comes out of the other side potable. And so the other small great thing about that first co-op was at the time, my grandfather, he also he's a mechanical engineer on my mom's side, and he was working in water filtration. And so
No kidding.
I was like, Grandma, for you.
That's a great connection.
That is a great connection. That's so fun. So, I mean, you went from water filtration to heat, right? So can you talk to us a little bit about Orion and how you got on that project and kind of what you do there for the Orion capsule? Yeah,
that's a very broad question, Jennifer. But I will try to answer it in a bit of a succinct way as best I can. Yeah. Throughout college, I was on a journey of what is it that I want to do, right? What is as an aerospace engineer? There's so many things you could do. I got very interested in guidance and control by the time I got to graduate school as a master's student.
Yeah.
And I love guidance and control. But I also love big picture. And while I took a focus for my graduate degree in guidance and control for entry vehicles, which is essentially when it enters the atmosphere, how do you steer it to make sure it gets to the spot it's supposed to?
Yes.
Right.
And I cut my teeth on some of the early development for Orion.
Wow.
So that's how I started off on just guidance and control for entry vehicles in general and on Orion. But through that process, I really focused on research on developing guidance and control algorithms. And in the process, you touch the heating part of the problem because you need to know, as the guidance and control person, what the resultant heating is for the trajectory you're flying. And that provides, it's kind of an iterative circle with respect to the engineers. Like, you could design the heat shield first, but then I have to make sure the trajectory actually doesn't overwork that thermal protection system, or I could design the trajectory and then the folks on the other side say, okay, this is the heating environment we're going to experience and here's how we'll design the heat shield. So it goes back and forth, right? So I've always had an eye towards the big picture, meaning I'm not just working on the guidance and control side. I care about what does it mean to the integrated system, the full vehicle?
Right.
Right.
So my career has really focused on guidance control, but then working in a broader sense on vehicle systems. And that's what the pterodactyl project behind me that I led was looking at that whole system.
Wow.
After I finished that project, then I had the opportunity to come on as the subsystem manager for the thermal protection system for Orion. And I am learning, this is what's beautiful to me about being an engineer, is every day I get to learn something new.
Wow.
And
That's awesome.
it is so important that throughout your sort of education and your early career days, you set sort of a foundation for yourself of the fundamentals that you can sort of get onto any part of the
Yes.
vehicle system and learn it. And it's been exciting. I'm not the expert, but there are some really awesome, smart people on our team. So I know you asked me about Orion, Jennifer, and I don't know if I've given you enough information about Orion, but I can launch into that unless Jeff has a question.
Actually, I was just going to bring us back to Orion specifically with, can you explain the thermal protection system, aka nicknamed the heat shield? Can you explain that to our listeners if they don't know it as well as we do?
Right.
Yes. All right. So for anyone who doesn't know, the Orion spacecraft actually has two components to it, a command module or capsule and a service module. And that service module has all the capabilities needed to take astronauts from launch or separation from the launch vehicle in space.
Right.
And take them to the moon and around, make sure they have all the water, the air, everything they need, propulsion to sort of send them around, and then bring them back home. And the astronauts, just to be clear, are living in the command module in the capsule, right? So now when the service module brings the command module back home, it separates, and now we have to get the astronauts through that last leg back down to Earth, right? That's one of the key things, and that makes space flight so hard or human space flight, I should say, is we want the humans to survive. It has to be a human-rated vehicle, right? So
exactly,
we want to protect them, right? Bring them back safely. So that last leg is pretty treacherous in the sense that, right, your gravity is now pulling the vehicle down.
Right.
We're also going at very high speeds coming back from the moon. Approximately 11 kilometers per second.
Wow.
And it's having to drive itself, or it's falling through an atmosphere, right? It's not the thickest atmosphere among the planets in our solar system, but it's thick enough that the heating is very, very high. And the extreme loads, the pressures, the shears on the vehicle are very, very high. So what that means is this command module that the astronauts are inside has to protect them.
Yes.
Right? It has to protect them from the heat and from the loading. Or I should say the vehicle has to withstand the loading. So what we do is we build a thermal protection system that can be installed on the main structure of the command module to ensure that the astronauts inside remain at temperatures that don't exceed maybe about 70 degrees F.
Wow.
But on the outside, the vehicle is experiencing up to 5,000 degrees F of temperature. So our thermal protection systems have to be able to handle and reject all of that, absorb or reject that heat in some way. Yeah. And that's the sort of main thing about heat shields that's really important.
Right. And so that people will know. So when you think of the capsule, it's sort of a triangle sort of thing. So it's the big base at the bottom, right? Is where the heat shield is. And so it's kind of interesting to me when you think about it, because when you think about doing something on Earth, if you're trying to move something through, you would turn it around, right? Because that's the smaller part. And so you get normally, but here.
Jennifer, what a great question. I love this question.
I always thought that was odd, but the reason why I'm assuming, and you can tell me if I'm right, is because the bigger base allows you to dissipate the heat a little bit better. Is that
so?
Is that sort of right?
That's sort of right.
Okay.
But there's actually two reasons why we're fat end down, right?
Okay.
So one is because we're coming in at such high speeds,
Yes.
we have to find mechanisms to decelerate,
To slow things down. Yes.
to slow things down. And so we call the capsule a blunt body. And so the ability for it to decelerate at the fastest rate possible is related to the large area that is on the front side, on the fat side of the capsule.
That makes sense.
It does also have the added advantage that you get larger area of heat dissipation across the heat, right? So all of that heat isn't focused at a point. So this is why, like, you would not send a pointed end in, right? Like from entry, it's just there's too much heat that would get generated on that sort of sharp edge, pointed edge,
right?
Compared to the blunt body.
So I was in the Navy. So when we think about pushing things through the water, we'll do it the other way, right?
Yes. You want it to be, I shouldn't use this word, and I don't know if it's how it would be used in water, but right, like just much like aircraft.
Yes.
You want it to be aerodynamic. So you're trying to make things as slender as possible and pointed it, right? Because that's how you make sure things move smoothly, right? In this case, we want to be fat.
Yes, because you want to help slow things down. No, I love that explanation. When I was a kid, I always used to wonder, why do they do it that way? So thank you for that. Now I know.
So I want to jump to the side just a little bit while we are talking about those heat shields, that fat end of the bottom of spacecraft. Obviously, ever since humans first started going into space, one of the main concerns was exactly what you said, Dr. Sarah, of we want those humans to come back alive. That was even part of Kennedy's speech of we want to send humans to the moon and they have to come back. Mission's not done until they come back alive. So from Yuri Gagarin and the original Mercury 7 astronauts, is Orion's heat shield very similar to what was being used back then? Or has technology really advanced what Orion has for a thermal protection system now? So
in terms of its similarities, the material we use for the thermal protection or the heat shield on Orion is called Avcoat. And that was used on Apollo as well.
Okay.
But over time, we've been able to, I want to say this in the simplest way possible. We've been able to make improvements to the mixture so that we can, manage what they call the thermal response, what the material does when exposed to heat. And so, you want it to have a certain density. You want to understand the amount of weight you're going to have to carry. So you're sort of trading all of these variables of we'd like a material that is lightweight, but also does the job of absorbing that heat, ablating off and getting rid of that heat energy. But both Apollo and Orion use the same material. The primary difference between the two is we're configuring it or installing it differently than Apollo did.
That was going to be my question. Yeah. How do you get this on the end of the spacecraft? Because it has to adhere and come off when it's supposed to, right? When it's as it's being burned off through reentry. How do you do that?
So very carefully.
Yes, I would imagine.
That's one of my favorite NASA answers ever. That was great.
So I have some really good, I've always thought about this, but really good examples of like just things we do at home.
Okay.
When, 3M has those like hook things that you can put on the wall.
Yes.
And what did they tell you? Did they say, wash the wall, make sure it's clean?
Yes.
And everyone knows when they don't make sure it's clean and they stick it on the wall, that thing falls off, right? Like it falls off, right? So rule number 1, we make sure those surfaces are so clean that when we adhere the tile or whatever that thermal protection system is, we are ensuring a quality that it will not fall off.
Wow.
So you can imagine that, that 3M hook has a tape, right?
Yes.
We use an adhesive. It has a quality to it that it can withstand a certain amount of temperature, right? Of heat. So you have this heat shield, right? It has some thickness. Behind it is this adhesive where it's stuck to our primary structure.
Right.
And you've got all of this heat transferring through the material, through the heat shield. It's not going to be as hot as at the surface. It can withstand a certain temperature that runs through the material. I don't mean to get too complicated, but
no,
that adhesive has to be, has to withstand a certain amount of temperature. So that way we don't have to make the heat shield so thick that we're using up a lot of mass, right? It becomes so heavy. So, we're trading this, like, we'd like to make it as thin as possible, but we also need to not break the adhesive right through.
This is where the material science comes in, right?
Exactly. Yes. Yes. So that's one, right? We've got to be able to adhere these tiles correctly. I was telling you guys the configuration is different between Apollo and Orion. Apollo had this honeycomb structure. So imagine a honeycomb, it's got voids, right? It's not full, it's structure. They attach that to the structure of the bottom side of the capsule. And then engineers took what I would call akin to caulking guns, right? Like, like your...
Oh, yeah.
Right?
Yes.
And they took the material and they inserted it into the honeycomb structure individually.
Wow. That had to take a long time.
It did. It was a long time to manufacture an Apollo heat shield. So that's the way they did it then. We, increased the size of Orion and decided that the honeycomb structure might not be something we want to replicate here. So we decided to do a tile configuration. So we build molded blocks of Avcoat.
Wow.
And then install those tiles. We have a set of center tiles on the bottom side, and then you have this circular infrastructure of tiles that go around. So what that also means is if anyone's laid tiled floor down, right? What do you have to do? You've got to grout between the tiles, right? You got to put stuff in between, right? We don't want any gaps. So we have to there's something called gap filler, and you put that in between each of the tiles. You have to also make sure that doesn't fail as well, right? It has to withstand certain temperatures. And what this all means is, when I was learning about all of this, I found it like really fascinating because you don't think about it.
No,
I don't. All of these materials expand and contract with heat. Right?
Yes.
Sure.
They don't do the same thing. So you also have to pay attention to the interaction between these, between each of these things, to make sure that there's no warping, right, that happens through that interaction.
Right.
So it's just, I took a material science class in college, and I was always like, wow, I had no clue. Like, I was like, wow, it's just so fascinating that you have all of these materials that can do all of these different things. And then you're like, man, the world is fascinating.
It is. It is. My son his undergrad was in material science engineering. And I remember going to visit Georgia Tech for like parents' weekend, and they took us down in the material science engineering lab. We just looked through the window. I was like, wow. But my son's looking at me. He goes, Mom, it's time to go. I go, I'm just going to stay here. I look at all these cool materials in here. I was like, why didn't they have this class when I was in college?
So you mentioned that the Orion capsule is larger than the Apollo capsule. And I've been lucky enough to visit Space Center Houston in Houston that has a mock-up of the Orion capsule out where you can see it and walk right up to it, look inside. And it does, in comparison to an Apollo capsule, it does look roomy. It looks, essentially like the inside, about the amount of space as the inside of a minivan.
Yeah.
Was the size difference a big engineering challenge for the heat shield, with Orion being so much larger?
That's a good question. The bigger size does pose a larger engineering challenge, because now you're not doing a 1-for-1 between Orion and Apollo, right? You're not like, oh, this is exactly Apollo. We just copy the blueprints, do the thing, right? That's not how. The other thing is, you don't have all of the engineers you had back in the Apollo days. And I cannot tell you how much I've learned about the people who build spacecraft, from the valves to the sort of making a gasket, they honed the perfection of any of these and systems and parts over time. And once they leave, right, you don't get that perfection back, right? Like it's gone. That sort of passing of the torch of all of that knowledge is all in papers now, right? It's not through the sort of passing it along in the labs, right?
Right.
So we are essentially, say, okay, we grew it. Now we're not going to grow the honeycomb structure. We're not going to, right? We have to now figure out what, for the size of this vehicle, is the best way to design and develop the heat shield for this application. So overall, I think growing the vehicle in diameter more than weight is where the challenge is.
Okay.
Does that make sense?
Yes.
Sure.
So I'm going to ask another part of this. So now that it's back, what are you looking for when you inspect it? Are you,
oh my gosh,
I know there's probably like lots and lots of lists, but can you give us kind of like, what are you mostly looking for? Like, did it stay intact? Is that the big check mark?
So,
or kind of like, what else are you looking for?
Yeah. So I love this question because this is the most exciting part. So one is the building, one is it flew and it did the thing and it came back and it splashed down. And now it's like, let's look at the data. Were we right? Right? Like all of our computer simulations, did all of our tests show us exactly what the system was going to do when it flew? So I'd say there are two things we're looking for, right?
Okay.
So one, I would say, is, did the inside cabin of the capsule stay at the right temperature, right? Did all of the heat projection and heat going to the heat shield achieve its goal? The second thing is, this heat shield is called an ablator.
Okay.
So the space shuttle was an insulator, which means it was able to be reused. It never lost a layer of material as it came through the atmosphere. So, but Orion is an ablator. Or the heat shield on Orion is ablator, which means as it's going through the atmosphere and it being exposed to heating, imagine the edges of your toast burning, right? In the toaster, right?
That's a great one. Yes.
It's essentially, as it's exposed to heat, it's burning and then coming off. So it ablates off, like it burns off.
Oh.
So when it's splashed down, what we're looking for is, were our estimates of how much of that the heat shield would burn off?
Yes.
Did we get that right? Did we over predict the thickness of the heat shield? Did we under predict?
Right.
We didn't under predict, but
yes.
But you're sort of looking at how much of the heat shield was left when it splashed down. Is that what we expected? That's probably the main thing that we're going to be looking for. And we instrumented this vehicle really well so that we have what are called thermocouples and some other sensors and devices that allow us to look at, they're placed at different thicknesses through the
right.
So we can have a point of reference of what was the temperature at each of these at different points.
Yeah.
What is the temperature? And if the sensor, doesn't give us a reading back at a certain point in the trajectory, that means we know that sensor got burned off, right? So it's it's been instrumented in a way so that we can really understand, what margin is left on the heat shield and how did it perform. And then, we'll look at other features. Right now, we're in the process of looking at all the imagery and trying to understand, the way it looks, did it do what we expected?
Right.
So it's really, really cool. From like an engineering solving puzzles and understanding, it's just really fun.
Yes.
The post-flight analysis.
So looking forward, there are more Artemis missions coming. Obviously, it wasn't just one and yay, we all saw a rocket and it splashed out. Yep. More Artemis missions coming. If the heat shield did with Artemis 1, if the heat shield did what it's supposed to do, will that be the heat shield that runs through the Artemis program? Or,
yes.
I was just going to say, or is there any reason that if it's doing its job, is there any reason to upgrade it or change its technology?
That's a great question. The way flight programs work at NASA, especially when we have all of these staged missions, is we're already building for the next mission. So the Artemis 2 heat shield is built. We've built Artemis 2. Whatever we learn on Artemis 1 can have an impact on Artemis 2, but it'll be very, very specific to what's doable, right? And what is its criticality to the survivability of the astronauts, right? So that'll be the main goal. So whatever we learn from Artemis 1, its impact will be seen on missions where maybe we haven't, the largest impact will be seen on maybe a mission where we haven't built up the heat shield yet, right? Or, or maybe you change something with respect to the operations. So what I would say is the heat shield, to excuse the pun, is cooked, right? It's already, it's already in there. So I don't expect major changes, but you never know. One thing that's really interesting about human spaceflight programs is we have brilliant engineers working through all the what ifs, trying to figure out how to design these well. But we're human. We can't know all things all at once. And I think one of the things that I've seen in various human spaceflight programs is you are constantly trying to get better. And sometimes you find something you didn't expect. And it can lead to a major change. And you have to sort of say, yep, we have to do this. Like there's no choice, even though you know it's going to extend the timeline or or whatever it may be, right? It's the right thing to do for the mission, right? So you do that. So, but right now I think we're good with the heat shield as is.
That's fantastic. Well, we could talk about heat shields and NASA and Orion forever, but we're kind of at that point in our show where we like to ask a guest for our challenge. Do you have a challenge for our listeners, Dr. Sarah?
All right. My challenge to the listeners out there is to find themselves some kind of curved surface. It could be a Frisbee. It could be a ball. It could be anything. And identify a material that they can make tiles out of. It could be pre-made tiles. It could be Play-Doh. It could be anything. And then find the best way to adhere those tiles to the curved surface that you have. And then see how much of your tiles survive when you drop it from, let's say, arm's length, when just hold it out and then drop it and see. And I think the person who does the best at this challenge will have, let's say 80 to 90% of their tiles survive.
That is a pretty big challenge.
I like that you gave them a number to shoot for.
Yeah, exactly. Well, this has been such a fantastic talk. Thank you so much for being on Solve for Kids, Dr. Sarah.
Thank you, Dr. Sarah.
I've really enjoyed it. It was really lovely talking to both of you, and I hope the listeners out there learned something, and thanks for having me.
Absolutely.
Thank you.
Sometimes these episodes are just not long enough because as Galactic Space Geek Jeff, I could absolutely talk about heat shields for a lot longer than we just did because humans are going back into space. And that heat shield is one of the most critical pieces.
Exactly. And I love all the physics and the engineering and the science behind this. And we got to get into all of that with Dr. Sarah. And what about her challenge? I want to know how many of you guys are going to try and find a material that works for your own kind of curved surface. Maybe you use an egg, maybe you use a ball, maybe you use whatever, and then put little materials on there to make your own tiles and then see how it works. How many of you are brave enough to test and see if your egg will survive a drop from space?
I can't wait to find out. I hope you share that with us.
Yes.
Because that adds a layer. A lot of kids and STEM enthusiasts out there have done that sort of lander. But we're doing it with flat cardboard on flat surfaces and single pieces. But when you add that curved effect, as well as that potential of adding tiles, that really changes the level of difficulty and really connects it to what the real world is doing with NASA and the Orion spacecraft.
Absolutely. So those of you that do this, which we hope you tried at home because science is best when it's in action, you can share your results with us on social media. We are at KidsSolve at Facebook, Instagram, and Twitter. Don't forget to check out our website, solveitforkids.com, where every episode has its own page with way more cool information on it than even what you get in the podcast. And thank you again for being such amazing listeners.
Yes.
And being with us these past 3 years. We are very thankful, and we're going to continue and keep having tons more awesome guests.
Absolutely. 3 years is just the start. Jen and Jeff are going to keep on going. There are so many more problems to solve. We definitely want to see you doing these challenges and sharing them with us on social media. Please connect with us. We absolutely love that. And with all the scientists, engineers, and experts that have yet to be on Solve It for Kids, Jen and Jeff are coming for you because you're going to be next as a guest on our show. Until next time, moving into our 4th year, you'll hear Jen and Jeff on
Solve It for Kids.